meetings. So hopefully this will be beneficial to you all. I'm not exactly sure what you all were expecting, but basically I put together kind of a summary of some of my research with kind of various advances in the field over the years. So hopefully it'll be helpful to you. So I'm a chemist. I'm a little bit different than many of the other speakers in this session.
I'm not going to tell you that again.
But I spent the first 20 years of my career at Argonne National Laboratory as a chemist doing research, which was really fun. And then about 10 years or so ago, I made a jump to the National Science Foundation. And so I am now a program director at the National Science Foundation funding materials research. But NSF does give us a little time to still go back and do research. So I enjoy dabbling in that, which is kind of a fun part. All right. So if somebody there's no clocks in here. So if somebody could tell me when we start, maybe give me like a 10-minute thing at the end so I can make sure we're somewhat timed. Okay. So I did want, those in advance.
If you click on the slide and press next, hopefully it'll work.
There we go. Okay, so I did want to acknowledge dedicate this talk to my longtime colleague, collaborator, many years ago, postdoc with me at Argonne National Laboratory, Jamie Manson, who's done a lot of this research with me, outstanding scientist in the field, but unfortunately he passed away last year from cancer, and so I certainly miss his partnership, as probably many of you do as well. And so, kind of going back to the beginning, this is the 15th ISCOM conference, as you're aware. It started in 1995 in Austria. Just kind of for reference, I mean, I got my PhD in '92, so for me, I mean, this has been kind of the conference of my lifetime. I've gone to as many of these as what I could. The last time that this was in the United States was in 2005, so almost 20 years ago. And probably many of you remember James Brooks, who is, again, no longer with us. But I mean, if you've never met him, I'm sure you never will forget him. He's excellent scientist and a really great guy. So, and I also wanted to, of course, acknowledge the chairs for this year's conference, Jan Musfeld and Tanya Drishku, who I've known for many years, probably at least a decade or so. A long time back, we've gone and done research together. I appreciate the things that we've done together in the research side of things, and for your efforts in putting together this conference and session today. And so the outline of my talk, I'm going to go through and give an introduction to crystalline organic metals, superconductors, and magnets, which is the theme of this conference series. And then kind of pulling out some dates and histories for those of you who might not have been around through the whole process of research. And then pull out a couple examples from my research that I think illustrate some points. And then I want to spend a few minutes at the end talking about the program that I run at NSF to show how that can help to maybe provide funding for this community going into the future. And again, I mean, I'm a chemist, I'm a crystal grower, or was, I guess, but still enjoy actually doing the chemistry and making new materials aspects of this research. And so, disclaimer, this is not a comprehensive review of the field, and many important details have been omitted, not intentionally, but just because of the time. And so I always kind of put this slide up at the beginning of talks these days. I mean, it's all of you presumably flew here. I don't know there's any other way to get to Anchorage other than flying here, but the engines in your jet planes, I'm not sure if you're aware, but they actually get within 90% of the melting temperature in those engines. And so the materials in them are very important. And if we look at the development of, if we look at the materials that were in there, the early studies started in the 1950s with microscopy studies and going through the 60s and 70s with alloy and property research, the 80s, commercial alloy process development. The first test engine was in 1993, and the first commercial service is in 2012. And so when we look at that, that's a 60-year progression from when the materials were originally developed to when they saw real-world applications. And I think that we really need to go faster. I don't have another 60 years to see things, end up in societal impacts. But taking a step back, and I don't think any of us were around in 1911, but this is kind of where I see some of the really beginnings, occurring. That Kimberlin Owens was very interested in the liquefaction of gases. And so, I mean, it was really cool back then to be able to, generate chlorine gas and then cool it down enough that it actually turned into a liquid. People initially didn't think you might be able to do that. But I mean, he liquefied various gases, pretty much most elements. And especially, I mean, the important one was probably helium. And so he was, liquefied helium with this liquefier. And I don't think he didn't really set out to discover a new superconductor. Nobody was really expecting what superconductivity was. But he was interested in measuring conductivity of various materials and, plotted or published this plot of the resistivity of mercury back in 1911 and was very surprised to see that it went to zero. And it was, approximately 50 or so years later that the microscopic theory of superconductivity was developed by Bardeen, Cooper, and Schlueter, for which they won the Nobel Prize in 1972. And so a couple of points here is I think that there's a value in having a broad perspective of science to be able to, understand the impact of discoveries, even if they're not exactly what you're looking for. And we also need to accelerate the time that it takes to go from, experimental results to scientific understandings. And so the first molecular metal, kind of skipping ahead about 50, 60 years or so, was TTF, TCNQ. And you can see the years that these molecules were first synthesized, 1962 for TCNQ, and Fred Wool synthesized TTF in 1970. And it was a few years later, 1973, when they actually mixed these two materials together to get this black precipitate, essentially, of TTF, TCNQ. And so this was the first observation of conductivity comparable to a metal in organic material. And really, the general design principle was that putting organic acceptors together with acceptors with donors, that you can make materials with enhanced electrical properties. This TTF TCNQ was really done by Ferris and Cohen in 1973, but also Heger published similar results also in 1973. And he, won the Nobel Prize in chemistry in 2000 for his work on conductive polymers, not specifically for TCNQ, but again, a very important part in the field of conductive organic materials. And I thought it's interesting now that this is actually an undergraduate collaborative that you can go to the Journal of Education and, find a undergraduate laboratory experiment to make TTF TCNQ. The first organic superconductor came a few years later in 1980. This is the TTF PF6. That was a superconductor at 0.9 Kelvin under 12 kilobars of pressure. And the following year, the ambient pressure version of this with the perchlorate anion was discovered. So these materials were grown by electrocrystallization, and that's kind of a technique that hadn't widely been used and still is not widely used for growing conductive crystals, but is really core to a lot of what's done in this field. I would say that it appears deceptively simple. I mean, I've spent most of my life doing electrocrystallization, and one thing you just mix these things together, apply current, and you get beautiful crystals to form. But as we'll see, there's many things that complicate that process. And I'd say that there are really limited studies that have been performed in really understanding the electrocrystallization process and how this occurs. And when you look up recipes in the literature, these procedures are often very generic, kind of giving a couple of reagents that they mix together, maybe a solvent, but not a lot of rationale as to why they were chosen or exactly how to grow the quality crystals. And so I think that advances in the field really begin, with improved crystal growth methods. And being able to scale up to grow larger, large crystals, quality crystals is important as well. And that's more than simply increasing the current density, the H cell volume, or the growth time. There's many other things that need to be considered, such as solubility, mass transport, surface chemistry, etc. So again, this is a core principle for growing new materials. I think that has a lot of potential, for the future to further develop. And so the most organic superconductors, probably maybe a correct statement, have extended this TTF basic framework to the BEDP TTF molecule. It puts this extra 6-member ring on the ends of the TTF molecule. And this provides, because of the extent of these sulfur atoms going further from the central core of the molecule, more lateral sulfur-sulfur interactions that result in more 2D materials, and probably contributes to the higher superconducting temperatures and more superconductors being formed. So the first organic superconductor based on ET was discovered in 1984, really with 2 phases of the ET-I3 material. The alpha phase has a metal insulator transition at 135 Kelvin, whereas the beta phase, as synthesized, has a TC of 1.5 Kelvin, but when you apply that slight pressure, half kilobar pressure, the TC goes up to 8 Kelvin. And it was understood fairly early on that these hydrogen bonding interactions between the hydrogens on the ethylene N group and the I3 anion are important for various purposes. I'm not going to really go into the details of that now, but with respect to the orientation of the ethylene group and other things like that. And so now I've probably lost count a little bit, but there are at least a dozen phases of BEDTTF salts known with polyiodide anion, because of all the different, I3, I5, and various other combinations of iodide anions. So these form as various different phases. In the early phases with linear anions are what's called the beta prime phase. These are dimerized ET molecules that generally exhibit antiferromagnetic ordering, like ICL2 has a temperature of 22 Kelvin. Under 82 kilobars of pressure, it does undergo a superconducting state at 14 Kelvin, one of the highest, probably the highest TC for an ET-based superconductor. The beta double prime phase, most of these are metallic to low temperature, and the beta phase, there are several superconducting salts. You can see here the ones that are symmetric were the ones that superconducted. The non-central symmetric ones did not superconduct. And so the general trend here was that the longer the anion, the higher the critical superconducting critical temperature. And so the thinking was that going to the longer anions would result in higher superconducting transition temperatures, possibly as high as 30, 40 Kelvin. And so a lot of other linear type anions were proposed, like copper thiocyanate, and you can read the list here. And so people set about to try to make superconductors with these longer linear anions. But what happens when you do that is that instead of getting the beta phase, you get a different packing motif, which is the kappa type salts. And 1988, superconductivity was discovered in the copper thiocyanate derivative of TC about a little bit over 10 Kelvin. In 1990, copper disalmon bromide and chloride salts were discovered to have superconducting transition temperatures in that range, slightly higher. The thing is that there's a lot of complications that go on when you try to do this electrocrystallization. And so in the case of copper disalmon and bromide, you have an equilibrium between copper bromide and dicyanamide in solution that can either get forced, to the right or to the left. And the desired phase is this one in the middle, but you can make phases depending on your stoichiometries in solution, like ET copper dicyanamide, or you can get phases that don't have any dicyanamide in at all and get a lot of these copper bromide type phases. In the case of copper dicyanamide chloride, you have a similar equilibrium, but the equilibrium lies farther to the left. And so, at least in my experience, and the predominant phase is more of these alpha copper chlorides, and then if you tweak things right, you can get the copper dicyanamide chloride crystals to form. And so I think the conclusion is that these complex anions result in numerous phases that form, and so this needs to be better controlled if you really want to grow the crystals that you want. So just a quick skip.
Look, that's Earth, isn't it? Who is that? Who are those people?
So ITC superconductors, as you remember, that was a look, I guess, from the, ages past, but, so, 1986 superconductivity was discovered in the cuprate superconductors. And I like how people, then were a little more, I don't know what you say, possible high T superconductivity in this, cuprate system. And so obviously Torres and Bueller were the ones who won, the Nobel Prize for their discovery of superconductivity in these copper oxide materials. And over the years, as you're probably aware, these TCs rose relatively rapidly. And to my knowledge, the highest TC in that group is currently the mercury, barium, calcium, copper. You can see these get pretty complex. That has a TC of 134 Kelvin, and this was discovered in 1993. And the question going kind of back earlier is that, well, what good is this? I mean, actually, I'm flying over here on the plane. The guy sitting next to me, he saw me working on my talk, and he's like, well, what good are superconductors anyway? I never heard of them. What do they do? Why do we care? So I told him, yeah, well, we can make, tapes out of these things and other whatnots. And so actually now at the National High Magnetic Field Laboratory, they have now used, tapes of rare earth barium copper oxides to make this 45.5 Tesla magnet, which is the highest DC field magnet currently, I believe, unless I missed something. So the comprehensive theory, again, people can debate this with me, I'm not a theorist, but the comprehensive theory of unconventional superconductivity is still kind of lacking a little bit, but these new nickel superconductors hopefully will help in developing that theory further. So superconductivity under high pressure, 2015, superconductivity was discovered in this sulfur H3 compound with a TC of 203 Kelvin, but under a huge amount of pressure, 155 gigapascals. And then the lanthanum hydride in 2019 with a TC of 250 K, once again under enormous pressure. And so, I mean, I pulled this plot, I think, off of Wikipedia or something like that. It kind of shows, the various TCs of various materials over the years. And as always, I'm disappointed they don't even put the organic superconductors on there, but we hopefully can change that. So, okay, so all of you might know what this slide is about. So there's also superconductivity was proposed in this copper sulfur hydrogen system, which is great because this is kind of what makes up ET, right? That has a TC of almost room temperature 287 Kelvin, 267 gigapascal, very high pressure, and followed by another, report of superconductivity and lutetium and hydride with TC of essentially room temperature under very low pressure, and the first, ambient room temperature, ambient pressure superconductor with that composition. Well, probably you all know. Just put a big X through all of those from all reports, and these papers have either been retracted or disproven. And so I think maybe they should have said possible superconductivity rather than superconductivity like the original groups. So moving on, again, I'm not going to have time to dwell on this, but I did want to, mention you all are, familiar with solid liquids and gases. And if you have the complement of this in magnetism or electronics, I guess you can get ferromagnetic materials or antiferromagnetics in the solid state, and the gas phase would be more like a paramagnet. But what's really interesting is, the spin liquid type states or dipole liquid type states. And so, again, I'm not going to go into this. I'm not, super expert in this area, but, I want to refer you to the Thursday morning session on spin and electronic liquids. And in this realm, ET does play a role that for, many years, this has been a prime candidate for a spin liquid, copper cyanide material, which also has a kappa type packing, but it was recognized, by Noda and others that, the spins here are located essentially on a triangle that could form a spin liquid type phase. And so this material has, again, a copper 1 cyanide anionic layer. There is disorder in one of the cyanide groups. And I don't know what else I wanted to say here, but this material does become a superconductor under slight pressure of 1.5 kilobar. And so again, refer you, I'm not going to go into so much detail, but there's a talk here at 11:20 that will go into this in much more detail. And hopefully this will just entice you about what was happening here. But in recognition to the work that was done by Martin Russell's group, somewhat more recently, was that he developed this broadband ultra low temperature ESR technique to be able to study these magnetic excitations directly from EPR. And so this anomaly that had been identified at 6 Kelvin for many years was identified as a transition to a gap magnetic state or a valence bond solved with these unpaired spins paired to copper-2 defects. And so there are copper-2 defects in these materials partially because of during the electrocrystallization process, you are doing an oxidation of a copper-1 system. And so some copper-2, will probably inevitably work its way into the crystals. But the silver system should be expected to be free of these magnetic impurities. And again, I'm not going to go into nearly as much detail as hopefully what Martin Russell will on Thursday, when I think he's going to talk about this in more detail. So shifting gears a little bit to some of the research that I was interested in over the years, was really interested in hydrogen bonding. I mean, we all know that hydrogen bonding is important in the formation of ice. If you're a biologist, it's important in biological systems, it's important in crystal engineering. But our question was really, how important might it be for organic conductors or magnets? And I'm going to try to touch on that briefly by giving a few examples from the bifluoride ligand or water hydride interactions, or the work that we did trying to put in anions specifically to increase the hydrogen bonding interactions with ET molecules. And so I also wanted to call out Mark Turnbull's talk on Monday morning, tomorrow morning, on hydrogen and halogen bonding and control of molecular magnetic materials, which I think is quite relevant, and hopefully we'll go into this in a lot more detail. But our approach is really to be able to look at two classes of molecular anions that could go into these organic superconductors that have a lot of electronegative atoms around it that could provide hydrogen bonding capabilities. And these anions could be designed and synthesized prior to the electrocrystallization process. So presumably we wouldn't have all the complications with trying to develop polymer type anions that I had described earlier. And so we took this one with the metal CF3 anion and crystallized it in a trichloroethane solvent. And when we looked at the crystals that we had, we noticed they're both plate-like phases and needle-like phases. And what we observed was that the needle-like phases grow first. And so if you turn up the current a lot and grow it fast, you got a lot of the needle-type phase. And if you grow them slower and with more time, then you get more of the plate-like phase. And so one of these is the kinetic phase, one is more the thermodynamic phase. By controlling the current density, et cetera, one can control what phase that you get. Well, kind of just skipping through and giving a high level talk, we found out there's a large number of materials again in this system. It wasn't quite as simple as what we had hoped. But if there are superconductors that form in this family, I think it's the most tunable family of molecular superconductors, or at least close to it. It's partially because there are three components, and you can't quite read it here, but it has ET, it has metal CF3, 4, and it has the solvent incorporated into the structure. And so there is a non-superconducting phase that the solvent doesn't go into the structure, but then there are two different phases here and here that are kappa-type salts that have solvent incorporated in them. The difference being the kind of whether the ET molecules from layer to layer are all in the same direction or go up and down, canting up and down with respect to each other. And then maybe more interesting is that the higher TC phase out of this group has kappa-type layers, but they're separated by charge-ordered layers. And again, based on the orientation of the ET molecules in the various layers, again, kappa alpha, the TC can either be 9 Kelvin or up to 11 Kelvin. And if one takes a quick look at the alpha type layers in these, you can see that the 9K phase has the charge ordering in kind of a stripe type motif, where if you have a spins on every ET molecule along the chain, I mean, this is reminiscent of a 1D Heisenberg chain that would be in the insulating layer between the presumably kind of superconducting layers in the ET salts. Whereas the 11K has a checkerboard type pattern of charge ordering in the alpha layer. I know I'm going through this kind of quickly, but it's kind of just an overview of things that have happened and that I've been excited about over the years. In 1996, we picked this other type of anion, the SF5, CH2, CF2SO3 anion that we crystallized with ET. And this one, again, forms a superconductor, TC, around 5 Kelvin. And it has, there is charge ordering kind of within the two different stacks of ET molecules. There's slightly different charge between the two stacks. And you can see that there is hydrogen bonding interactions both within the anions and between the anions and the ET layers. A couple of things that we liked about that these are, it has a highly tunable anionic structure, so you can make a lot of chemical modifications to this structure. There's also no copper 1 or actually copper 2 impurities, no copper impurities in there because we don't have transition metals. And a single phase form, so we don't have to worry about polymorphism in the system. And so, again, just quickly, these materials are really ideal systems for looking at things like the FFLO state and superconductors. Originally, this lack of a 90-degree peak in the interlayer transport was a sign these are highly two-dimensional materials. And then specific heat measurements indicated that they were prime candidates for FFLO in organic superconductors. And so again, I refer you to more details to Professor Rugi's talk, which is Thursday morning, cycle before noon. And I think he's going to talk more about the FFLO state in his presentation. But just to show how this can be further investigated, these are with laboratory scale magnets because the energy scales we're talking about here, our temperature is kind of more like, 2 Kelvin or so, and fields that are made up to 10 Kelvin. So by studying the NMR either as a function of temperature or a field, one can see how the FFO state develops as you go into this region of the phase diagram. And so again, if you're interested in that, I refer you to that talk on Thursday morning. So if we look at dimensionality of molecular superconductors, we've talked about the 1D materials like TMT, SF that have TCs closer to 1 Kelvin. The 2D materials that are based, many of them on BBTT type structures, materials. And then the next candidate would be the C60 materials that have TCs as high as 38 Kelvin. And so superconductivity, once again, a little bit of history, was first discovered in C60 materials with K3 C60 at 18 Kelvin. That was really kind of fortunate in my career because it was about the time that I was finishing my PhD and I went to Oregon to kind of work on superconductivity and these Buckminster fullerenes. And then the highest TC in this class, and once again, is the last expanded, the TCs would go up, and the highest TC for fullerenes now, I believe, is cesium-3 C60 with a TC of 38 Kelvin. However, there was a report here in 2001 about high temperature superconductivity and last expanded C60, where they could interpolate in other molecules of the last to be able to get to TCs as high as 117 Kelvin, but probably many of you realize that that's also a fictitious result. And so you can kind of be aware of these things that sneak into the literature sometimes. And I wanted to throw out this other example too of treating superconductivity in the Piscenes that are in the, around 2010 or so. There were quite a number of papers that came out with superconductivity reports in, potassium, barium, type doped acene materials like this. This one paper has over 400 citations of superconductivity in that system. And these are, to my knowledge, the 7 molecules that demonstrate superconductivity that had TCs up in the range of 35 Kelvin or so. It was quite intriguing. However, this is largely now believed that these are not superconductors. You can see this paper by Crystalline and others that have basically made these materials. I mean, it's not entirely ruled out, but I mean, it's just has not really been able to be reproduced as described. And so I guess the thing to learn from this is that it's not, a lot of money and effort and things are wasted by these kind of, fictitious results that show up in the literature. Some of these statements here is that in order to make these hydrocarbon superconductors, you really need a lot of effort from the experimental side, especially with respect to growing high purity crystals. And so a lot of these results we've done on polycrystalline materials are probably impure. And so really the value of growing high quality single crystals is important. And so just to show you that these sort of things can be done, I mean, this is some work that we worked on at Argonne, was growing crystals of reductively doped crystals of these materials, and you can actually grow crystals of them, not of the specific ones that were supposedly superconducting, but you can make materials like this that may have interesting properties. And we didn't really probe what these properties are, but there's obviously a large family of these materials that can be investigated in single crystal form. So I think there is some research that comes out of this, some fundamental knowledge regardless. And so how am I doing on time? 5 minutes. Okay. So I'm not going to really be able to cover this too well. I was going to talk about molecule-based magnets a bit, but I'll just kind of skip 10 minutes. Okay, so I'll spend maybe 3 or 4 minutes on this, and we'll skip then to the end part. But molecule-based magnets, there are things that are really molecule-based magnets that I would say are molecular transition metal clusters with organic ligands. And that might be what you would actually call a molecular magnet. But coordination polymers are materials where you basically take a transition metal and you link it together with some kind of a ligand, and it's going to form either one-dimensional, two-dimensional, or three-dimensional type structures. And so, again, I think there's a lot of exciting stuff here, both from the magnetism and the conductivity aspects. And I refer you just simply to the Tuesday morning session on MOS if you're interested in that. I'm not going to have time to go into this as much detail as I'd hoped, but again, we had worked in the area of looking at copper fluoride coordination polymers because of their possible, as possibly being analogs to cuprate superconductors with strong magnetic exchange through the bridging fluoride in between copper type systems. And there's a lot of chemical challenges in these materials because the fluoride acts considerably different in many ways than what fluoride or bromide does. It has promotes strong hydrogen bonding, has low solubility in water. Fluoride will interact with your glass vessels, and it provides various issues with respect to toxicity and other things. So there are complications there chemically, but I think a lot of potential. And so I'm not going to really have time to talk about this, but we were very interested in looking at the effect of the Jahn-Teller distortion in copper based coordination polymers and how we can control the Jahn-Teller axis and the magnetic orbitals. And so this is kind of a question that I would kind of throw up is in, what direction would the Jahn-Teller axis lie if you have a trans octahedra that has oxygen, nitrogen, and fluoride around it. And, there were essentially no answer to that question in the literature, but really the answer is kind of all of the above. And to just quickly explain what happened is we made this copper fluoride hydrate pyrazine coordination polymer, and we noticed that there's a series of pressure-induced phase transitions. And what happens is that you're basically, as you pressurize the material, you switch the direction of the Jahn-Teller axis, and this can transform a two-dimensional magnetic material into a one-dimensional chain. And so we can control, the orbital order and magnetic properties if we can control the orbital orientation of the Jahn-Teller axis. And again, I don't have time for this right now, but I did want to call this one slide that kind of describes the characterization of this copper fluoride hydrate pyrazine coordination polymer both at high fields and by using muon spin relaxation, because there are 2 talks also in this conference, the one 8:40 tomorrow morning by John Singleton of ultra high magnetic fields, and the one by Steve Blundell on Monday at 11:30, I think, of the same session using muons as a local probe. And so I would encourage you to listen to those talks as well. And we have some work here on the bifluoride ligands, which I'm not going to really be able to explain other than the fact that by controlling the synthetic conditions, you can either make a phase where all the Jahn-Teller axes are aligned in one direction or where they are alternate, like along Z and along X, and that has implications on the magnetic properties as well. And I'm probably going to skip this one for the matter of time as well, but it's basically putting fluoride into the Herbert Smith type structure to be able to control the packing. So where do we go from here? I would say that superconductivity is no longer the sole driver for future research. Many new themes and drivers have emerged. And I think you'll hear about those at this conference. TTF salts, I believe, provide an element toolbox for realizing and understanding novel properties of these materials. Certainly from my perspective, crystal growth is key to this process, and we need to better understand, spell that wrong, with the electrocrystallization process, the selective crystallization of desired phases, and the mechanisms for being able to grow significantly larger crystals. I also wanted to call out the opportunities of data science that you probably have noticed, that development of high throughput experimentation can help to accelerate materials research and potentially in the future, even autonomous type research. And I would say in that respect, I mean, how much unpublished data do each of us have? That could really benefit the community. I know that I have piles of data that have never been published that really should be out there somewhere for everybody to benefit from. And I have probably maybe 2 minutes left, and I was going to talk a little more about this, but as I mentioned at the beginning.
You got about 7 minutes now.
7.
10 minutes for questions afterwards.
Okay. Well, I'll leave a little time for questions.
For 7 more minutes, we're talking about 10 minutes left.
Okay.
So yeah, a little more time.
So if you'd like to hear any of these topics, I can talk to you a little bit more about you during the conference. But as I mentioned, my day job right now is program director at the National Science Foundation. And so I kind of wanted to give a little bit of a perspective on kind of what's happening there and what our thinking is. But I lead the NSF's part of what's called the Materials Genome Initiative to be able to help businesses discover, develop, and deploy new materials faster and cheaper than what's available through current, methodologies, in a way that this is being done. Just bringing together experimental tools, digital data, and computational tools to develop what we call materials innovation infrastructure. And so if you're interested in learning more about the Materials Genome Initiative or the Design Materials Revolutionize and Engineer Our Future program, I would call you to the initial white paper, the strategic plan from 2014 or the strategic plan from 2021, about a decade in, that really talks about the importance of unifying material innovation infrastructure, harnessing the power of materials data, and educating and training the next generation of materials workforce. And as I went back to the beginning, I mean, we know how long it takes to be able to go from the discovery stages to eventual deployment. This can oftentimes take many decades, and NSF, it kind of goes through various divisions of NSF. And we kind of envision thinking about how all these different parts of discovery, development, property optimization, manufacturing, et cetera, will eventually come together to be able to have societal impact of the materials discoveries that are being made. And so the program that I manage at NSF, covers really all material classes. So, we fund work in quantum materials, photonic materials, magnetic materials, and pretty much every other material that you can think of. It is a program that crosses about 10 different divisions at the National Science Foundation, most of which are co-funded by multiple parts of NSF. And so it's not only about the materials being studied, the materials and scholars who certainly fit into BMREF, but it's about the philosophy of being able to integrate experiment with computation and data. And we encourage, proposals that are high risk, high payoff. We think that in general, people are too conservative about the type of work that's being funded and done. And so a traditional research approach would look kind of like this, where you synthesize material, you go in the lab and make a measurement, and then you find your theorist friend down the hall who can explain the properties that you observed. But the MGI approach is being able to put this into a feedback loop where theory makes a prediction, synthesize, synthetic chemists will make the material, and the experiment will validate the prediction. And then hopefully the theory can improve for another cycle of that loop. But we always need to kind of keep an eye on what, societal impact these materials might ultimately have. But the thing that's missing from all these things is really data. And in the traditional approach, the synthetic people will make their synthetic recipes, and the measurement people will have their piles of data, and the theorists will have their data, but they don't really overlap with each other. And so in the MGI philosophy, the data kind of sits in the center of this cycle, where the data is really shared between the theorists, experimentalists, and synthetic people, and not only within the project, but ultimately within the community as a whole. And so again, just throwing out some places you can look at if you want to learn more about sharing data. There's a study that we sponsored on building a materials data infrastructure, and a second study on artificial intelligence for materials and manufacturing. And as many times we bring in partnerships with mathematics, statistics, and computer science. And so, again, these are some reports that you can find at their website, demref.org, about meetings that we've had. If you're curious about the program, I encourage you to go to the demref.org website and can find project summaries, publications, and highlights from all the projects that we've funded over the years. The National Academies recently completed a study of the DEMREF program, and one of the recommendations they made in here was coordinating activities among international initiatives to align with best practice in sharing data, not only within the U.S., but, with our partners around the world. And so we're working to do that. And you may have heard of a term called digital twins. I don't know if you're aware of this, kind of a tetrahedron for materials, but on the experimental side, it brings together processing structure, properties, and performance through characterization. And then there could be, in principle, an equivalent matter in the virtual world to be able to design materials in silico that would hopefully be able to help predict which materials to make and how to make them. So I know I rushed through that pretty quickly, but our next DEMREF competition will be in January of next year. Encouraging partners between simplest experiment and theory with federal partners and with international partners as well. And I'm not going to have time to talk about some of these various highlights of work that might be relevant here, but these are some of the brightest fluorescent molecules that have been discovered in DEMREF. This one actually is about building a database of organic semiconductors. I wanted to call your attention to Chuck Augusta's presentation this afternoon at 3 o'clock on his ideas to build a database for crystalline organic conductors and superconductors, which I think will be very interesting as well. And this is kind of a highlight about making completely organic batteries, the importance of batteries and electric, everything electric these days as well, and clean energy. So these are my final thoughts. I'll wrap up. Sorry, I rushed through that end part a little bit quickly, but I think that significant progress has been made over ISCOM's first 15 years. Looking forward to the next 15 years to see, the advances that you all will be making. There's really a ton of scientific challenges that require material innovations, and so I encourage you to really, attack those, with vigor. These partnerships and multidisciplinary research is critical. You can really no longer just go in the lab and do, your own research just, in a vacuum. I really need to work out and connect with theorists or experimentalists, data scientists, mathematicians, engineers, et cetera. They can make the most of the research that's being done. I think I've been able to illustrate a little bit the importance of integrity and trustworthiness in research, that, a lot of efforts, a lot of dollars have been wasted on scandals of incorrect reports. This probably always happens, publications, but we need to really consider that, the impact of that going forward. We should take advantage of new tools, whether they be computational, experimental, or synthetic. There are really new tools being developed in all these areas, but intuition is still vital. I don't really think that theory would have, for example, discovered this superconductor or predicted this on its own, because it's kind of in a corner of the world that, that you wouldn't really maybe think about putting together, but it seemed like there were reasons that we should look in that direction. But so I think the combination of theory and intuition is critical. Also, the access to dark data. These are all the kind of what we might call failed experiments, where people will do experiments and they don't get the results they want, and they don't publish them because they're not so bright and shiny. But really, to be able to make the most of data science and data type tools, we really need to have both the failures and the successes. Crystal growth is really more important than ever. We really need to know, how to put atoms really where we really want them. I also would encourage this high risk, high payoff science. I think that scientists, reviewers, and funding agencies often tend to be too conservative in their approaches. I mean, I see that, when I hear review panels, a lot of times they'll say, oh, this is great, but it would probably never work, so we shouldn't give it money. And reviewers always want to put the money on the thing that's, well, there's a track record that for sure this is going to work, but that's kind of easy, the low-lying fruit. And so really, to make the step type advances in research, I think that we need to take high risk and potentially the high payoff, of course, to go with it. So that's partially where I think program managers have to come in and kind of make those decisions. But and finally, molecular systems hold much promise to think outside of the, think outside the box. Just don't follow along with the traditional ways of doing research. And my question is, could we be entering this new, golden age of superconductivity and magnetism that could be fueled by computational, the use of computational experimental tools that now exist that didn't exist, many years ago when I was starting research. So I rushed through a lot there. Hope we covered a lot. Again, very high level. I'm sure that I missed way more than what I included, but hopefully it gives you a little bit of an overview of what my perspective as a chemist was and a little bit of what my thinking is as a program manager of the Science Foundation. And I'm here all week, so hoping to take happy to take questions now or anytime during the week that you're around. So thank you for this time.
All right, we have about 7 minutes for questions. So does anyone have any questions for John?
You put the so-called fake signs on the finite field superconductivity of 100 something on 1060 sort of together.
Oh,
But one set was a genuine mistake as far as I know. Because I knew the people, the finite field stuff. Whereas the other one
yes.
was not a mistake. So there's
Right,
a
right,
difference
right.
between fake signs
Yes.
as opposed to mistakes.
Yeah, I did kind of throw that one on the side there, and I didn't mean to make the implication that it was all fabricated. Thank you for bringing that up, but there is both the examples of where certain scientists have fabricated things and published it as being great work, and there's other cases where I think the scientists have done what they consider to be good work and somehow got a result that was very intriguing and published it through reviewers, and it turned out that there were various impurities or whatever in the technique that led to incorrect conclusions. And so they are different cases. That is true.
Any other questions? Okay, next. Go back, yeah.
Okay, then you start your talk about talking about superconductivity discovery due to serendipity. Then you start the talk about serendipity, and you end the talk about intuition. What happens then? We need serendipity here, or we need intuition?
So
Then we are evolving from serendipity to intuition,
I
or is the reverse?
so I think the two go hand in hand, that you kind of need. I mean, you can't control. I mean, serendipity is kind of what happens just kind of out of the blue, but you need to be able to recognize that. But I think that
But this is more important.
well, more important. Well, I don't think we want to rely on serendipity. That would be a little risky. I don't want to fund proposals where people are relying on serendipitous results. But I think that we want intuition. But I think that the point is that we want to be able to recognize when we see an important result that might not be what we're expecting, and not simply to discard it because it wasn't where we were planning to go. So I think that, clearly serendipity plays an important role. Most of these superconductors that have been discovered, I don't think I actually said that, but the one hydride system, there was probably the first example of really where a prediction was made that was validated by experiment. I think that was maybe the only example of superconductivity in a new class of materials that was actually predicted before it was made. Pretty much all the other ones, maybe people had an inkling maybe to look at superconductivity in C60, but it wasn't, it's kind of a little bit more like try and see what happens.
The other is first serendipity, after intuition, and after rational. Well, the last example is rational. In a rational way, you have
Rational. Yeah.
Rational
Right.
is more, not intuition, but is rational. You can predict theoretical work, for example. Rational.
Rational would be presumably what a computer would, right? And so that is
What we think also.
or within, but a computer might be able to do it faster, maybe. So rational, certainly, I'm not proposing,
Rational design.
saying you're rational
You are
design.
saying all the time, we are saying all the time, rational design.
Rational design is great, right? We need rational design, and computers will probably help us do that better and faster than most of us can, but people who have intuition hopefully can be in the loop, to help decipher which rational things, for example, the computer would think is a good result, and you intuitionally say this is not feasible. And so that's kind of where rational approach and the intuition approach is there. And I guess, we leave some room for serendipity, because if we don't have serendipity, we would not probably have most of these superconductors. So,
We got two more questions here, one here and one in the back.
Somewhat more question you mentioned, at one point you were exploring different annihilators to become particular based on. Is there any method that you use to, to choose what annihilator to explore?
so I mean, I guess that's a question, about how much intuition you really have. I mean, so when I was doing this research, I mean, I couldn't really predict like what was going to make a kappa type packing motif versus a beta type. I mean, there are a lot of now structural prediction programs that can help with it. There's many polymorphs out there that even if you get a beta phase, there might also be a kappa phase that you can grow. So that's hard in your mind to predict. But I think that what we were trying to do is to find to use the design principle of using hydrogen bonding, for example, interactions that would help to be able to stabilize materials with desirable properties. And so we were kind of using the hydrogen bonding approach to be able to somewhat control these interactions, even though I couldn't obviously predict, whether you put a certain anion with it, what kind of packing motif it's going to give. I mean, computers can help with that these days, but again, there's many polymorphs that are possible. That depends how hard we do it.
Final question in the back.
Yeah, John, I wonder if you could say a little more about this tension between high risk, high reward science and kind of standard, more traditional science from the student point of view. Because, this is a student tutorial session, and I mean, speaking for myself, I always worry how some really bold new idea would play in front of a review committee. But for a student, there can be a lot of risk with, this really most exciting science. And I wonder if you have any advice for them in that regard.
Well,
Go for it, or pull back, or use
well,
them both.
I mean, I understand what you're saying, because this is an issue, because I mean, a student wants to get their PhD in X number of years, and if they have a lot of failed experiments, so to speak, that, I mean, they took a lot of risks, and maybe they did, maybe they don't, so that is a lot of risk there. But I guess that what I would say is that you can probably, I don't know what the correct saying is, but you can make good things out of somewhat failed experiments that you had a grand plan of how this is going to lead to the next, room temperature, the first room temperature superconductor or something. And so you had this wonderful plan. I mean, kind of like I was talking about with the alkali metal doping of these, icings and things like that. So, I mean, so none of that stuff for me turned out to be superconducting. That was kind of our goal, was to make these higher temperature superconductors. But it's still a project that's generating new science, new understanding that can be published. And so I think that it's worth taking some risk to try to have these big discoveries. But they, of course, many times will not work out the way you expected, but that you still get intriguing results that can be published, and hopefully, put you on your career for the future. So I guess that would be the advice I would say, is to try to make the most out of things, even if they don't give you the results that you were hoping.
All right, everyone, let's give John another hand clap.
So